Hi guys, today I have a nice differential equation here, um, and we have some bounds that we have here, some restrictions, such that we have a set here that's an ordered pair that has bounds for x and y, and we also have this variable m here, which is assigned to some manipulation of the Euler's formula for a sine cosine. And as the follows go, we need to find something as the instructions go. We need to find what f is. Um, Great. So let's just hop right into this equation. So this differential equation. So first, what we're going to do is we're going to subtract this side on and put it onto this side. So this term here that has this m, we're just going to slide it over to the other side, and so we just have this partial f. We should write it just a little bit less big. Partial f with a dx, and then partial f with a dy, with this y cosine 3x here. And we have this minus x squared minus this 1, this m, 1 plus x squared over 1. Great. And so now what we're going to do is we're going to cancel out this term here on this side. And in order to do that, we just multiply its inverse. And then we're going to multiply that inverse on this side. And then after that, we're going to then multiply and we're going to separate these differentials. Great. So let's do that. So what we get in turn is this cosine of 3x e to the minus x squared minus this cosine of 3x. And now we're going to say this, the y at the bottom, and then there's a y 1 plus x squared at the bottom here. And this is all multiplied by a dx dy. And so these would just go over to this side. Now what we're going to do is we're going to take the integral of this side here and this side here. Great. And so let's just do that. So we're going to take the integral here. It's a big integral. And we're going to take the integral here. But we know that there are bounds and restriction from a set. So because we're taking the integral of x and y on this side, we have to use the restrictions that we have for x and y. And so we have the set C that is operating on this integral for their bounds. And so in this side, we'll just evaluate this. And then we will have the C operating on this side here. And so you have a cosine of 3x e to the minus x squared over y dx dy minus this integral c here again with this cosine on the top and with this y and m at the bottom with the 1 plus x squared dx dy. And so now what we're going to do as follows. We're going to do this integral in respect to the y, which is the first part. And we're going to evaluate this part because it's the easier side. And this will just evaluate to ln. And so the bounds just shift. It will just be ln of y with a 0, not a 0, a 1 and an e. And because we can recall here that the bounds for the y is 1 and an e. Great. And so now we could go back here and we can now evaluate this part. We know this is just going to cancel into, well, that is huge, into 1, because ln of e is 1 and ln of 1 is just 0. So we have this 1 term here. And recall the Euler's formula that we've manipulated is actually cosine of 3x. Why? Because if we have the Euler's formula here with 3x, the coefficient in front will then evaluate, will then cause the coefficients of the function's x term to be amplified, like so. And since it's just a subtraction on this side, we know that this term is going to be equal to 3x, which means that the 3x, the cosines here will cancel out, and now we're just left with the integral of 1 over x squared. And if you're familiar, we know that this will actually evaluate into tan inverse of x. And if we evaluate this from 0 to infinity, it will be approximately equal to pi 1/2. Great. And so now we will put that in. So now we're done with one part of the integral. And for this next part, I'm going to actually change the color to red. And so we have f. Just recall the entire thing. And we have this c. And then we have this nice little, what is it? Cosine of 3x e to the x squared, the y, and then we have dx dy minus pi 1/2. Great. And so now what we'll do is we're going to evaluate this integral now. And for this, I'll actually assign it to I. So now this integral will be a function of I. And so we're going to do that. This c cosine of 3x of e minus x squared over y dx dy. And I will evaluate from y first. Okay. And so let's do that. And so we'll just get ln of y evaluated at 1 and e. So we know that's just going to be equal to 1. And so we could just say, great. So we just have this bounds for x, which is just going to be cosine of 3x e minus x squared dx is equal to I. Now, one of my favorite techniques is going to be used here. It's called the Feynman technique. Technically, it was not necessarily developed by him. It was being used by mathematicians before him, but he's the one who popularized it. So for all sakes and purposes, I'll just be saying it is Feynman technique because that is how people know it. And it goes as follows. You get a variable and you assign it to some constant within the equation that you're integrating. And for this case, it would be 3. And from there, what we do is we differentiate in respect to that variable. And so we treat everything that does not house that variable as a constant. And so that means this will transfer into minus sine of x e minus x squared dx. Great. And so from here, what we'll do is we'll assign this to dv, and we'll assign this to u, and we'll evaluate from there. So if we from here, if we assign this to dv, we can imagine this as a u, so we use nice u substitution. And if we u substitute that, and then we plug that back in, we know that these x will cancel out, and there'll be a 2 at the bottom. So what we'll do is we're going to say, great. We'll have the minus sign bit here with this minus x squared over 2 evaluated at this integral of the derivative of this part, which is just, well, this will now become positive, which will just be cosine x e to the minus x squared over 2 dx. Now, first and foremost, we will evaluate here, which will just collapse to 0 because it converges to 0. So we can just say that's 0 here, the zero's out. And then we will make a nice little observation that this integral here is actually just 1/2 of the integral that we started with before differentiating it in respect to that variable. So we'll just say is equal to 1/2 I. And so we'll just divide I and multiply this differential at the bottom here. And so we'll say I over di, which is equal to this part here. If we evaluate it, which will just be 1/2 this, and then we'll take the integral of this part, ln of I, and we'll have a nice little 2 at the bottom, and then we have an e, so we could get that integral again, and so we have this I is equal to e, and I forgot the plus c. Don't forget that plus c. Okay, so now we have this beautiful looking equation, and we want to get this c sort of component of this equation by itself per se, or with something else. So one way to do that is to collapse this into 1, and to be able to do that, we need to set this equal to 1. I mean to 0. And that will also have some implications in this I. And if we recall what I was, we know that cosine has that variable inside, and we know it's multiplied by the e to the minus x squared. So that means that we will now have the integral of, because cosine at 0 is 1, of minus x squared dx, which will then look and develop to this EC. Now, another interesting thing is that this is the Gaussian integral evaluated from 0 to infinity, and that is equal to the square root of pi over 2, because we know that this is equal to just this. We divide it, divide by 2, it will just be equal to this. Great. So for some clarification. Okay, great. And so we know e to the c is equal to the pi over 2. And so now we can recall the entire thing that, now we can recall this integral. And so now we know the actual value for this integral, which is e. If we put that constant equal to 3, because that was the original constant, so it'll be 3/2, and it will be pi over 2. Great. And so now we actually have the integral's value for both. And so let us just recall the entire thing now. We're going to use a nice yellow. So it's f over 2, which equals to this new thing here, which is pi over 1/2. And then we'll have this minus pi half here. And we're going to just solve for f at this point. And so just multiply the 2 and then square root that f, and we get f is equal to the square root of e32 pi minus pi. And there we go. That's how you would solve this integral for f.